This module is the beginning of the section of direct look-ahead approximations. This is the first module. We're going to break this general strategy into 5 different components. Direct look-ahead approximations is the policy that I like to describe as what you do when all the others don't work. And it's often the case that all else often doesn't work, and we end up doing direct look-ahead approximations. So this is going to be part 1, overview of direct look-ahead approximations. We're going to talk about types of look-ahead approximations. This is a equation that you've seen before. We have the immediate contribution from making a decision now, and then there's the downstream. Now, that downstream, when we do DLA policies, this is where we're actually going to have to roll up our sleeves and get into this model of the future. When we did VFA-based policies, we just waved our hands and says, okay, this is just some function. Now we're actually going to get into this, so we need to walk through and understand this better. So again, if I'm here at the square node, I'm in a particular state, which can be very complicated, and I'm going to make a set of decisions. X can be discrete, but it can be vector, it can be continuous. I want to find the best decision. After you make the decision, random things that can happen. Again, these can be very high dimensional. And then you have all this stuff in the future. Now, as we go into the future, depending on what decisions I make, and then depending on what random outcomes happen, I have to make decisions in the future. Now, I've already decided that I need to do a look-ahead policy, but I can't generally do a look-ahead policy for every possible decision node in the future. Remember, I'm not going to implement those decisions in the future. I need a reasonable approximation. And of course, we have the downstream random outcomes. Now, what we're going to do is we're going to create what's called a look-ahead model. The look-ahead model, if we have our base model of states, decisions, and information, the look-ahead model is also going to consist of states, decisions, and information. So it's the same SXW notation, but notice that I've changed it. First of all, I put tildes on all the variables, and then all the variables have 2 time indices. This is a look-ahead model triggered at time t. So the first time index is time t. I'm planning into the future from time t. The second time index is t prime. I'm looking at time t prime in the future. That's me planning into the future. Now, there are different ways to do these approximations. First of all, when I look into the future, I can do a deterministic approximation or a stochastic approximation. I can truncate the horizon. I can do different types of discretization of time, state variables, and decisions. The policy. I'm decided my problem needs to plan into the future, but as I plan in the future, I need to understand decisions that I might make. How we make those decisions is what I call the policy within a policy. Latent variables. I may have variables that are changing over time. They're part of my state variable. They're important. But when I plan into the future, I'm willing to hold them constant. And if you take a variable and hold it constant, it falls out of the state variable. At that point, it becomes a latent variable. It drops out of the state, and we effectively are fixing it. It's like a fixed variable in S0. The random information, I can do all kinds of approximations using outcome aggregation and different sampling methods. And finally, there's a subtle approximation that we will illustrate later called stage aggregation. And let me defer to later to describe that. So now I have my look-ahead model, which is state, decision, information, but with these tildes. I've thought about what I need to approximate because every problem's different. But I have looked at my problem and says, okay, I think I can get away with certain approximations. There are going to be problems where a deterministic look-ahead is fine. There's going to be problems where it's terrible. So it's very problem specific. You have to look at your problem and think about what are the approximations I can get away with that make a reasonable trade-off between modeling accuracy and CPU times. Let's assume I've come up with something that I'm happy with. So I use my approximate look-ahead model, plan in the future, make a decision now, roll forward, update everything, repeat it, plan in the future with my approximate look-ahead, do this over and over again. So at the end of the day, my look-ahead is just a policy. Yes, I'm doing a lot of possibly complex calculations, it's still just a policy. There's a lot of work in stochastic optimization where what people are actually solving is a stochastic look-ahead, but it's still hard to solve. And so researchers will say, oh, here's this stochastic optimization problem. Actually, it's just a policy that needs to be solved over and over again. So evaluating policies, let's say we start at time 0 in our initial state. We use our look-ahead policy, whatever it may be, to make a decision. Now new information comes in. I step forward, let's say to time t, repeat the process all the way out to time capital T. At some point I have to end my simulation. I'm going to look at how well I did each time period. If you sum these, recognizing that these x's are the result of the policy, that's the performance of the policy, the look-ahead policy. Okay, very important to understand this because there are so many papers out there, and including entire books, that will do a stochastic optimization problem. They'll put uncertainty into it. It's still hard. They still have a nice challenge. They don't recognize that what they're solving is still a stochastic look-ahead, and it matters. So DLA policies are widely used under different names. In operations research and other fields, they'll call it a rolling horizon procedure. In computer science, they'll call it a receding horizon procedure. The control theory guys love to call it model of predicted control, and that's because they're using a model as an approximate model of the problem to plan into the future to help make the decision now. So they call it MPC. It sounds fancy. I like to use the phrase direct look-ahead approximation because it's self-explanatory. All right, let me talk now about the policy within a policy. So when I'm going out in the future, all those squares, I have to make decisions. I have to do it with some policy. What policy should I use? Again, these problems come in many different flavors, and so there isn't any single answer. But guess what? We have 4 classes of policies, and we can choose from any of these 4 classes of policies. Sometimes it'll be obvious which to choose, but not always. By the way, value function approximations, I can point to no shortage of papers where I can say, look, you know that value function approximation, it's really a VFA policy in a look-ahead model, okay? And we've overlooked it. But anyway, we can really look at all 4 classes of policies. Now, the question is, well, wait a minute, I've already decided that I want a DLA policy for my problem. Why aren't I just using a DLA policy in the future? The answer is often because it's too expensive. I have many possible states in the future because of simulating all the possible sources of randomness. Furthermore, the decision I'm going to implement now, I really want high quality, whereas decisions in the future, I'm not actually going to implement those decisions. I just want to make sure I don't ignore that there's a decision. And so the trade-off between quality of the decision versus computation changes in a look-ahead model. Now, the effect of suboptimal policies in the look-ahead on the quality decisions is an open research question. It really hasn't been investigated to any degree in the research literature. Okay, this brings to an end